Welcome back, everybody, to episode 28 of the Quantum Science Seminar, which will today all be about circuit QED. As usual, we would like to have your questions. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. If you would like to join us for a discussion with our speaker after today's talk, please use the Zoom link that I will post in the YouTube chat at the end of the talk. Also note that there's a 30-second time delay between what you see on YouTube and between what we do. And with that, I'm going to hand over to our guest, Serge Rosenblum, who will introduce our speaker today.
Thank you, Sebastian. It's my honor to be introducing Robert Schoelkopf to you today. So Rob is a Sterling Professor of Applied Physics and Physics at Yale University, and he's also the director of the Yale Quantum Institute, as well as the founder of the quantum computing startup company QCI. So Rob is one of the founders of the field of superconducting quantum computing, and his lab at Yale University is among the most influential labs in the field worldwide. So among his many breakthroughs are the invention of the entire field of circuit QED, Quantum Electrodynamics, which studies the interaction of artificial atoms and microwave resonators. And he's also the inventor of the transmon qubit, which is the qubit that is used in virtually all superconducting quantum computers today. So I'm not going to bore you with the list of awards that Rob has received, but just very briefly, in 2017, he got the Connecticut Medal of Science. He was also awarded as a member of the National Academy of Science in 2015. And together with the other founders of the field, Michel Davray and John Martinez, he got the Fritz London Memorial Prize in 2014. So with that, I hand the stage to you, Rob.
Great. Okay, can you guys hear me? Thanks everyone. Thanks for the kind introduction, Serge. It's nice to see you all virtually, and it's a pleasure to be able to give this talk today. So I want to start by acknowledging, all of my colleagues and collaborators over the many years at Yale, Michel Davray, Steve Gervin, Liang Zhang, who's now moved on to Chicago, and the many others who've helped us and made this so much fun over the years. So this is a very exciting time for our field. I'll start with maybe a brief advertisement. So we have a new organization that I'm part of. It's called the Co-Design Center for Quantum Advantage. It's one of the new DOE national hubs, part of the U.S. quantum initiative here. And maybe just a word or two about kind of where we are in the field today and things. So the first word in this name of this center, co-design, this is a term of art in conventional computer architectures and supercomputing. The idea is to now advance quantum computing to the sort of post-NISQ age by looking at the linkages between algorithms, quantum computer architectures, error correction protocols, and of course the devices and all the stuff that underpins that. And so you can have a look at the activities in the center and the many participants there. And we're definitely looking for talented students and postdocs in my lab and in many of these other labs here. So please check us out. Here's the little menu of what I thought I would cover today. And we're going to try and do this in enough time that there's room for questions. Plus, I guess I can also stick around for some Q&A afterwards. I guess since it was expected, there'll be a little bit of the standard introduction and reminder of some of the basic concepts in circuit QED. Then I'm going to focus on what I will define the strong dispersive limit of circuit QED and how we're able to use nonlinear superconducting devices like the transmon qubits to do some quite remarkable manipulations, control, and measurements of quantum harmonic oscillators, which usually we make with microwave cavities. And then what I thought I'd really focus on is a recent set of results from my lab, where we use these capabilities in circuit QED to do Gaussian boson sampling plus more, and how we experimented with a particular application of that for a class of simulation problems, basically calculating the vibronic spectrum of real molecules, which I think is kind of a nice instance of this idea of thinking about the use case for a quantum simulator or a quantum computer, the particular algorithm, gate set, routine that you use to implement it, and then linking that all to the full stack, as it were, and the strengths and capabilities of the hardware itself, which I think is really what we need to do if we're going to make these quantum systems, really useful for things outside of course, all the wonderful quantum physics that we know and love and that drew us to this field. Okay, so, and I will try to pause a little bit for questions during. I think there's a way they're going to be collecting these and so on. So to begin with, just sort of basic primer here on cavity quantum electrodynamics. This is one of the sort of signature model systems in the field of quantum optics and atomic physics. It's a very interesting but simple system where we have a nonlinear device, an atom, a two-level system or a qubit, and a bosonic mode, an oscillator of some sort. It could be, an actual atom inside a pair of mirrors in the optical, or it could be in the microwave, as we'll talk about. And when we put an atom inside of a cavity like this, there can be a dipole interaction between the two, where now, for instance, the atom can emit into this cavity mode, or it can absorb a photon from the cavity mode. And the kind of key energy scales and time scales of the problem are the so-called vacuum Rabi frequency. It's the strength of this coupling term here between the field mode and the atom, or the nonlinear device. And the most interesting limit of cavity QED comes when one can achieve strong coupling. If this coupling between the atom and the field mode is large compared to, let's say, the rate of decay of the photons or decay of the atomic state, or other decoherence mechanisms like the atom falling out of the cavity, then one can actually use this interaction to entangle the 2 degrees of freedom, and that allows exchange of information and lots of interesting kinds of quantum manipulations. Okay. So in particular, in this strong coupling limit, if one can arrange that the cavity mode is resonant with the atomic transition or the qubit transition, then one has this kind of case. This is all very well explained in this beautiful book by Serge Haroche and Jean-Michel Ramond, 2 of the biggest pioneers in cavity QED, which I commend to you if you're a new student and you're wanting to learn about this stuff. But we have basically now, 2 states, depending on whether our 2-level system is in its ground or excited state. But we also have a set of photon number states, some ladders associated with the oscillator. And in this case of resonance and strong coupling, what happens is this state where, let's say, there's an excitation in the cavity, and this state where there's an excitation in the atom become resonant with one another, except that there is a degeneracy that's lifted by this vacuum Rabi coupling. And now the real eigenstates of the system are going to be sort of the bonding and anti-bonding states of the qubit and the photon, which we sometimes call the qton and the phobit. And if one would prepare an excitation either in the cavity or in the atom, you would actually see kind of coherent oscillations between these 2 energy eigenstates at a rate g. And so, as Serge was alluding to, one of the things we started thinking about with Steve Girvin, Michel Devray, and others back in the early 2000s was how to realize this exact system in the microwave domain, where we can use a Josephson junction device, originally a Cooper pair box, these days a transmon, or other superconducting nonlinear device that plays the role of the atom. microwave resonators that can either be strip lines or, as I'll show later, three-dimensional cavity resonators that play the role of the field mode. And this has some wonderful advantages. We have the ability to replace all the lasers with much easier microwave signals, which allows us to very rapidly kind of iterate on things and add very fancy kinds of controls, which are possible, but I think just more expensive and more difficult to do in the optical domain. But also what we can do is get very strong confinement of the field and very strong interactions between our atomic degree of freedom, or the qubit, and the microwaves. And that's kind of what's allowed circuit QED to do a whole lot of new things in quantum optics, and also then can be extended to building quantum computing experiments and platforms. So the thumbnail sketch of how superconducting qubits work, the heart of all of these superconducting devices is a Josephson junction. This is the PowerPoint version. You have just two superconducting electrodes with a thin barrier, which allows the tunneling of the Cooper pairs. And ideally, we would think that well below the transition temperature, this device is dissipation free. It's kind of naturally gives a capacitance, plus the tunneling of the pairs means there's a Josephson inductance, which means that we've already built a sort of electromagnetic oscillator where, however, the inductance is nonlinear due to the fact that we don't have a linear current phase relationship here, but the sign coming from the Josephson effect. And what this means is that we actually have something where there's a kind of energy potential, which is more like a cosine. And that gives us an oscillator or a ladder of states where we can have a large frequency difference between, let's say, the transition to go from the ground state to first excited state and the transitions to go higher up this ladder. And so typically we build these devices to have resonance frequencies of 5 or 10 gigahertz, which means that a single photon, a single quantum of microwave energy is a fraction of a degree Kelvin. But if we operate in dilution refrigerator, we're essentially at zero temperature, and all of this microwave domain can be quantized. And so now, this can be your 0 and 1, or your spin down and spin up of your two-level system. Effectively here already, your ground and excited states are sort of presence or absence of, as I mentioned, one quantum of electromagnetic energy or one microwave photon. And there's some really nice advantages here that for these transmon qubits, you can have anharmonicity here of hundreds of megahertz, so that we can do fast operations in some timescales on the order of nanoseconds. And we can have pretty long coherence times or very low dissipation in these devices because it's all superconducting and at low temperature. And so the kind of default standard qubit now in the superconducting world is this transmon qubit, which is basically just this nonlinear oscillator that I mentioned on the previous page. It's realized by having this Josephson junction plus this kind of structure, which can either be on chip or it can be a three-dimensional device fabricated kind of just with two electrodes that are longer, that gives the capacitance. And then this is the real picture of a Josephson junction. They're made in a fairly standard way now with 2 layers of aluminum, a thin thermally grown aluminum oxide barrier between that allows the tunneling of pairs back and forth here and gives this, this inductance. And what's really nice in circuit QED is that if you couple this device to one of these strip line transmission line resonators, you can achieve a very strong coupling. So the vacuum Rabi frequency 2G here can be sort of on the order of hundreds of megahertz out of the overall photon energy, which is a few gigahertz. That is to say, we can have coupling strengths in a sort of dimensionless sense that are a few percent. And so if you remember, the idea was it's more interesting to get to the strong coupling limit. That means even when we have quality factors of a few thousand for either the superconducting qubit or the cavity mode, we're already in the strong coupling limit. And for aficionados of this field, sort of typically now in our 3D implementations of circuit QED, we get cooperativities, or kind of the ratios of this coupling strength to the net dissipation that can be, 10 to the 10 or something like that. It's extremely strong coupling. Okay, and that's because we're sort of cheating, because the coupling itself is naturally just so strong. And so, yeah, there's a lot of things that one can do with this. You can, of course, use the coupling to the microwaves through a sort of transmission line structure like this to entangle qubits that can be centimeters apart or even further on a chip. You can also use the coupling to these microwave cavities as a method for doing very good measurement and so on. And so this has made this whole system very interesting from the quantum computing point of view. I'm not really going to focus on that too much in today's talk. I'm giving another online talk, which has the acronym VAMOS, I think, next week. And I'll try and leverage a little bit off of this basic introduction and talk a bit more about some of the recent experiments we've done in quantum computing and quantum error correction with these systems in that talk next week, if you'd like to hear more. So, one of the key things when we started in this field, it was not even clear that you could make a qubit or anything that would have a simple Hamiltonian that an atomic physicist would recognize, let's say. That question, can we really make a man-made object that has a well-defined Hamiltonian and manipulate it? That's been answered now very much in the affirmative. And we've seen, very rapid increases in, let's say, the lifetime of both cavities and qubits here, getting up to the point now where we can have millisecond sort of, millions of nanoseconds of coherence time. And again, since sort of a few nanoseconds to a few hundred nanoseconds is the typical time it takes to exchange information between these degrees of freedom, or to do, fundamental gates or operations. This means that we really have reached a point where it's possible to do error correction, and someday to build, really large scale and very complicated quantum machines out of these devices. But you may also notice, by the way, that this plot I'm showing here has a right axis, which is 2015. The progress now, as everyone has been focusing on scaling up the complexity of their machines and the number of elements, not as much energy maybe has gone into continuing this trend to improve coherence times. And you always want to have, more dynamic range between your gate times and your fundamental limits. You would like error rates to always be slower and fidelities higher at the physical level. And so that's something that we continue to work on. And that's another big focus of this DOE hub, because I think, continuing this trend is important. Otherwise, we sort of will run out of gas at some point. And many other things in this field have advanced remarkably. In the beginning, it was a heroic effort just to detect a single qubit. These days, we can even do things such as this, which is sort of showing here two particular time traces of the quantum state of one of these superconducting qubits, where it's just being weakly driven between its ground and excited state, or spin down and spin up. And in this case, we're using a parametric amplifier that's also made using Josephson junctions. In particular, these were really championed in the modern era by Michel Devereux and then many others, which now gives us the ability to measure, you see here, with very high fidelity, the state of one of these qubits in a few hundred nanoseconds, to the point where in this time trace here, you see we have really wonderful resolution on sort of individual quantum jumps of one of these single superconducting qubits. And the ability to do a QND measurement on one of these qubits is, of course, essential for doing quantum computation or quantum error correction or all of these other things. And so there's been many, many orders of magnitude of progress in our ability to how quickly and how accurately we can measure these devices, do the controls, and all these other sorts of things. Okay, so maybe this is a good point to pause and see if there's any questions on this preamble or introduction. And then I'll talk a little bit more now about how we utilize and control oscillators, and then move on to this quantum simulation application.
Yeah, Rob, so far, not really questions from the audience, but maybe I can drop in one.
Go ahead.
Because you were mentioning that you passed actually the scaling threshold for error correction. What is actually the state of, at the moment, the status to demonstrate actually useful error correction? Right, where the logical qubit error then is lower than actually the error that you have.
Right. So, yeah, the threshold, of course, is a strong function of the error correcting code and scheme that you are using, right? What I had on this earlier slide here was sort of a notional thing saying, well, oops, you know, if the gate time is some tens of nanoseconds, in many of the schemes, you know, 10 to the 4 gates per error, but of course that's just a single qubit gate, is acknowledged as, you know, at least good enough. In some other schemes, such as the surface code or the surface code with biased errors, you could get by, the threshold is maybe only a few %. But you would like to be well past this threshold and have a fault tolerant device in order to realize true gain in error correction. So what I would say, and I'll talk a bit more about this in my talk next week, our effort at Yale, we've come now to the break-even point where applying error correction on several operations, a memory function. Also, we've reached break-even in quantum communication, where we can also use an error correctable word that we send over a coax between 2 blocks in the cryostat. And in the paper by Serge, when he was with me, we demonstrated the ability to do error correction on a gate performed on a logically encoded qubit, where we start to see the sort of reaching the break even or the very beginnings of gaining from the act of error correction. The problem with error correction in general is that it's more complicated and there is an overhead, and things get worse before they get better. So reaching break even is sort of like getting to loop gain of 1 in an amplifier. And of course, what you want is, you know, loop gain of 1,000. And so that's the goal. But that, you know, is now, I think, understood as, you know, both one of the really interesting scientific challenges and one of the technological, you know, barriers here that we need to knock down to really make all of this fully scalable. So we're a little bit of a ways from full fault tolerance, but I believe it's possible, and I think it's coming in a few years.
Okay, many thanks.
Yeah.
No questions otherwise, so I will...
Okay, maybe people are shy, or maybe they've heard this whole story many times before. My apologies if that's the case. So let me talk a little bit more about why we're so interested in the oscillator degree of freedom and how we use that more and more as kind of the object we're more interested in or is more useful to us than even just the transmons, although they remain a very important part of the operation. So first of all, as a reminder, right, a cavity has more resources than a qubit. It has multiple energy levels. It's got a bigger Hilbert space all within the one device. And here's a sort of picture of how we actually realize some of our best cavities these days. They're kind of machined out of a piece of aluminum. They're a 3-dimensional sort of coaxial stub resonator. And with these, we can actually obtain quality factors of 10 to the 8 or more. That is lifetimes of several milliseconds, which is like an order of magnitude better than the very best transmon qubits that are out there. And so this means that we have some advantages. We have the long lifetime. We have multiple levels. We also know with these cavities that they basically have predominantly one error channel. It's just that the quality factor is finite, and so you lose photons one at a time. And for error correction, that makes this a much easier and better system to start with, because you have less things that can go wrong. It reduces the threshold and the complexity of your error correction gadget. Now, this linear oscillator, though, is not that useful all on its own, because you can only create sort of semi-classical states, coherent states or the like inside. And what you really want to do is to be able to do arbitrary control over this large state space consisting of the potential 0, 1, 2, 3, up to n photons in this object. And so the way we do this in our labs is using kind of a combined platform of cavities. Here's a block showing 4 of these cavities, and we can couple them to transmons, which sort of serve as the ancilli in the error correction scheme, or as the control and input-output mechanisms for the manipulation of these cavities and the kind of simulations I'm going to tell you about. And you can have these transmons which couple to an individual cavity, or even that have kind of a Y-shaped antenna like this that will couple to multiple cavity modes at once that allow us to turn on and off various kinds of nonlinear interactions within the cavities and between the cavities. And that's the basic gist. And what's nice about that is that you're protecting yourself to a certain degree from the actual errors and imperfections of the transmons all on their own. And in this platform, by the way, we can make this kind of resonant vacuum Rabi interaction, but more and more we work now in the case where, let's say, all of these cavities may have rather distinct frequencies that are several hundred megahertz apart, and the transmons will further be at some distinct frequency, which is strongly detuned from any of the actual resonance frequencies of the cavities themselves. And that means that we're going to work in this dispersive limit of circuit QED. So if you start with the Jaynes-Cummings-Hamiltonian, and now we introduce a detuning, see, I sort of defined that, a detuning between the cavity mode and the qubit mode, this capital delta here. If we make that large compared to the vacuum Rabi frequency, so that's a few hundred megahertz or more compared to this vacuum Rabi, which might be 50 to 100 megahertz. Then basically there is still a coupling between things to second order in perturbation. You will have this, we call it chi dispersive shift, which is proportional to g squared over delta. That's just obtained by sort of looking at the large detuning case of this Jaynes-Cummings-Hamiltonian. And in that regime, we have still our field mode and our cavity. They're sort of primes here because now these modes are dressed, and there still is a little residual coupling between them. And now the main term, however, is looking like this. It's parametrized by this second order coupling strength chi, and it takes the form now of A dagger A times sigma z, or it's, you know, the number of excitations in the field mode multiplied by the number of excitations in the qubit mode. And that's a very interesting thing. For instance, if we look at the qubit absorption frequency, what we find is now, you know, there is a particular frequency that it takes to excite the qubit from G to E. I had these spin up and spin down before, but same thing. If the cavity is empty, and there will be a distinct frequency separated by chi or 2 chi for exciting the cavity if there's 1 photon inside or 2 photons. This is the so-called strong dispersive limit here, where this frequency shift of one mode due to the quanta added to the other mode is large also compared to any of the decoherence rates. And this sort of photon number splitting was first observed, you know, several years ago in 2007, but it gives us some quite interesting and amazing capabilities. If you like, you can think about, you know, if we now applied a microwave pulse, let's say at this particular resonance frequency, we can do things like flip the qubit or control its state, conditioned on there are exactly n equals 1 photons in the cavity. And this allows us, you know, more and more over the years, we've explored a whole host of ways that we can manipulate not just the qubit, but the cavity in kind of surprising ways. So let me give a little example of that. So again, we have, now I'm going to go into the rotating frame of both the qubit mode and the cavity mode. We still have this interaction term, which is sort of doubly QND, frequency shifts only of the 2 components. And we can apply some arbitrary microwave drives at both the qubit frequency and the cavity frequency. And what we can do is we can throw this Hamiltonian into a computer and ask it to build a complex operation for us. Let's say I want to climb the photon ladder in the cavity by 6 rungs all at once. I want to go from the vacuum to n equals 6 in the cavity. Now the computer, this optimal control, tells us we should do the following amplitude and phase modulations on the qubit and cavity drive, which are not very intuitive. But as soon as either of the systems is out of its ground state, there's going to be this interaction, which is going to mean that the qubit and the cavity will become entangled with each other. So I'm going to show you here the Wigner function conditioned on the qubit being in the ground state, or the Wigner function sort of conditioned on the qubit being in the excited state, as we kind of play through this pulse. So let's see if the animation here will work. The drives turn on, the cavity moves around, crazy things are appearing. And in the end, in this particular instance, we started in vacuum in the oscillator and ground state in the transmon. We wanted to return to ground state in the transmon, but to have placed 6 photons inside the cavity. And this is what the predicted Wigner function should look like at the end. When you do the measurement, you see now that the qubit only absorbs at a frequency which is displaced by exactly 6 times this dispersive shift. And if you measure the actual Wigner function, that's real data, you get this beautiful thing with 6 rings, which is preparing n equals 6. And so this capability to kind of rapidly create a highly non-classical state in your oscillator, including like funky things that are superpositions of photon numbers for encoding logical information, this is a really great capability. I saw some stuff in the chat. Do we want to maybe pause here and take some questions?
Yeah, sorry, yes. So there's one question floating around, and that's basically, well, I'm not sure that's actually the right point to ask, because it's a little bit off topic what you're explaining, but it's still about actually an analogy of your coupled in the end coupled qubits to the Bose-Hubbard model. And the question, if you can realize the Bose-Hubbard model, and if you also could realize a Fermi-Hubbard model with this.
Definitely yes on Bose-Hubbard. We're actually thinking of some particular experiments where you can use the qubits to engineer, let's say, the nonlinearity, which would be the on-site interaction. And then some of the stuff I'll show you here of swaps between modes is like the coupling or the hopping. I think there are theoretical ideas about how to do fermions as well. But let's stop there, and maybe I need to pick up the pace slightly here to get through what we wanted to talk about. So next week I'll talk a little bit more about the use of these capabilities for error correction and how we can make a sort of hardware efficient scheme for error correction, where this single bosonic mode serves as the logical and the transmon as the ancilla, replacing a lot of other much more complicated schemes if you're using sort of traditional qubits. And what this part now of the talk is a little bit about how we can also try and take advantage of the capabilities of the hardware and the fact that we natively have these very nice bosonic modes with long coherence time and good measurement and manipulation capabilities to do some kind of quantum simulation that's a little bit more efficient. And in particular, what we're going to do is calculate the so-called Franck-Condon factors in the vibronic spectrum of some simple molecules. So as you've probably heard, kind of quantum chemistry is a very important field where people are hoping that there are real uses now for quantum computers. And so, you know, the interesting thing here, right, is that even for a very complex molecule, we think we know what all the atoms and the constituents of it are. We know the governing rules are just quantum mechanics. How come we can't just put this on a computer and solve ahead of time for the right catalyst or reagent that will cure COVID or something like that? And the problem is that although this is just a quantum problem, for real molecules, things get quite complicated, right? And it requires an exponential scaling of the classical compute power to, you know, sort of do the full quantum treatment of a molecule. And so why use a quantum computer? Well, because you know, it has naturally that quantum capability, and you know, it has this sort of exponential power, which is the same thing that makes the quantum chemistry on a conventional computer difficult. And you know, mostly people think about using qubits or two-level systems as the elements in the quantum computer to, you know, emulate or calculate the properties of a molecule. Now, the molecule has many interesting degrees of freedom. There could be actual spin degrees of freedom. There's the fermionic degrees of freedom. Where are the electrons in the orbitals of the molecule? But there are also things like the vibrations or configurational changes of the molecule, which are naturally a bosonic degree of freedom. And you know, to make a long story short, there's actually significant overhead in mapping the number of orbitals or the number of vibrational degrees of freedom onto a bunch of spins, which is, you know, we haven't yet achieved quantum advantage in quantum computing, where we really do a quantum chemistry problem on a quantum computer that you couldn't do on a conventional computer. And, you know, this is particularly the case for doing the bosonic or vibrational problems where we have the possibility of many quanta. That means we would definitely need many qubits or spin-a-half systems to represent even just the behavior of a single stretch mode of a molecule. And so what are the kinds of things we would like to do? Well, I mean, there are chemists, and now at Yale, we've been collaborating quite closely on this work with several of the physical chemists and the computational chemists that we know here on campus. They might do something like this. They you know, go in the lab and measure this kind of complicated spectrum for a molecule. This is actually, when I'll show you the photo emission spectrum of H2O. And this spectrum is complicated because it's got both electronic and vibrational degrees of freedom that are coupled. And you know, what one would like to do as a chemist is, you know, make a new molecule or look at some unknown molecule and then go from all the information that's obviously present in this spectrum backwards to the molecular properties. And of course, similarly, you say, what would the spectrum, how would the spectrum change if I make, you know, this atom now deuterium or something like that. And I'll just give a little quick introduction here to these vibronic spectra. So kind of picture looks like this. We have, let's say, as a function of the separation between two of the atoms in this molecule, we have some sort of potential energy surface that is created, and of course an equilibrium position for the location of these two atoms due to, you know, all the bonding that's going on by the electrons inside the molecule. And if we, you know, zap this thing with a laser, we can make a transition from the electronic ground state to an excited electronic state. But once you do that, you also change the forces on the atoms. And there can be, as I've sort of tried to draw here, both a shift in the location and potentially also a change in the restoring force or the potential or the vibrational frequency that you might get of these atoms in the molecule. And even if we just, excuse me, make a harmonic approximation for this, when we zap this thing with a laser, we can make a transition, let's say, from the vibrational ground and electronic ground state, potentially to any of these electronic excited states with different number of vibrational quanta inside them. And so to predict and understand one of these spectra, you want to understand these weights or the probabilities of making a transition at each of these frequencies separated by this vibrational quantum in the molecule, the so-called Franck-Condon factors. And to do this, you need to first solve the fermionic problem, computing the potential energy surface, and solving that to get sort of what these force fields are. That's done by classical or potentially by quantum methods. But then you also need to compute these overlap integrals between all of these eigenstates to obtain the actual peak heights and locations in the spectrum. And that requires sort of recursive algorithms and can lead to a sort of exponential number of overlap integrals in principle that you need to calculate. And so what we're going to show here is a way to get those Franck-Condon factors directly using a quantum simulator. So again, the goal is to know these overlaps or Franck-Condon factors. We kind of were inspired by a proposal from Asper Guzik and co-workers for how to do this in linear optics or microwave platform. One wants to basically apply the kind of basis change going from this set of vibrational states to this one, and then measure the overlaps. And it can be done using the so-called Doktorov transformation, where we have displacements, squeezings to represent the change in frequencies, and rotations. In the multi-mode case in this molecule, one of these stretch modes now might actually get mixed up with the other stretch modes in the molecule. And so the requirements to kind of do this calculation are, we would like ideally to have native bosonic modes, so we've got those. We need Gaussian operations like beam splitters or mode mixing. That's this rotation matrix here between the modes, squeezing, displacements, as well as preparation and the ability to measure the number of quantum in the end. And that's sort of something where we have very nice capabilities here in the microwave. So here's what we're going to do. We're going to simulate the spectra of some simple triatomic molecules where they have just basically two dominant vibrational modes. Like in water, it's this symmetric stretch and bending mode. And they're going to be represented by two of the microwave cavities in this transmon plus 3D cavity platform here. And okay, so we have these capabilities. We have the ability to use the Josephson junctions to engineer the right kind of couplings to do that operation. And the point here is, it doesn't matter whether we're simulating the infrared vibrational quanta of this molecule, doing it with an optical quantum computing platform, or doing it in the microwave, because there's just a way we can scale out all the energies and do that. Okay. So here's again the platform. There are two of these modes. There is associated with each of these cavity modes an ancilla transmon and a readout channel that allows us to detect the state of the transmon and therefore the cavity. And there's also a nonlinear transmon device here that couples to the two, that allows us to do the interactions between these two modes and entangle them. And basically we can prepare a variety of initial states using this optimal control techniques I showed you before. We can do displacements. That's very easy, just driving on a microwave pin the cavity modes. That's one of the other Gaussian operations. And then we can also do, even between these cavities, which are at two different frequencies, a kind of beam splitter or A dagger B kind of interaction between the two modes by the right combination of applying two microwave signals to this intermediate transmon. We have four-wave mixing that gives us this kind of interaction. And we can also, with different frequency conditions, engineer a nonlinearity or a squeezing here in this individual cavity modes, A and B, that allows us to adopt or account for the change in frequencies in this vibrational problem. And, long story short, all of these operations can be done in a time that is short compared to the actual kind of native decoherence times. In fact, in this bosonic platform, we have pretty good ratios of gate times to decoherence times. The final ingredient here that I want to describe is the ability to do measurements. I kind of alluded to this before. Again, if we have a mode and we want to know how many photons are inside, the qubit has this dispersive coupling, which means its frequency is shifted by a certain amount. That's our dispersive Hamiltonian again, chi, depending on the number of quanta that are inside this. So the first kind of measurement we can do is we can query to say, do you have n photons? So, let's say this ancilla is known to be in the ground state. We can apply a pulse at the correct resonance frequency where, it's omega naught minus n chi, and detect his state, which will give us a click or not that says, yep, there were 5 photons in the cavity. Or no, there are not 5 photons in the cavity. What we really want to do in this Franck-Condon problem is we want to say, how many photons did you end up with in the end? That's the answer. And what we can do here, which is kind of neat, is we can actually do a sequence of measurements on this cavity using the ancilla that will give us more than one bit of information. We can collect a string of bits which correspond B0, B1, B2 to the sort of bitwise number decomposition of the state. So 6 would be 0, 1, 1, 0. And we can do this sequence of 4 measurements using, again, some combinations of these optimal control pulses to basically flip the qubit if and only if, let's say, you were an even number of photons or 2, 6, or 10 photons and so on. And we can take a sort of unknown P of n, and in the end, at the end of this measurement, we will collapse on a particular photon number, let's say n equals 6. And here's just kind of an example of preparing a simple state, a coherent state, which has on average 7 photons. And we can do this bitwise measurement and then look at the result. And you see we can sort of sort the coherent state into its Fock components here by measuring the Wigner functions after this actual measurement. Okay, so this is pretty handy because now it means we can actually just go ahead and do the Vibronic simulation. So we start in a particular state, actually in the ground state, let's say, of both cavity modes. Say we want to know the Franck-Condon factors from going from the 0, 0 state to one of its electronic excited states. There's a simple gate sequence, which I've represented here, which consists of a couple of squeezings, some swap or beam splitter interactions between the modes, and then some final displacements. And then we do this bitwise number measurement, and we extract out basically the number of photons in each cavity. Then we repeat this with several shots and look at the probability that, let's say, we get 5 and 5 in the 2 cavities. That corresponds to the Franck-Condon transition probabilities of going to n equals 5 and m equals 5 in the final configuration of the molecule. And by using this bitwise number reconstruction, we actually get make this whole procedure scalable because in each preparation of the state, we basically get out the full photon number. So we get a sort of acceleration factor here, which is quite significant. In these experiments, I guess I forgot to mention, for example, in water, when you make this particular transition, you actually have probabilities of exciting up to a few dozen vibrational quanta in the molecule. So here we're also really employing the larger Hilbert space or dimensionality. The state we're ending up in is something in this 256 dimensional Hilbert space, and then we want to, actually figure out what the photon number in each of the cavities are, and from that, what the vibrational spectrum is. So this is sort of the, basically the calculated classically is the solid black line, and then the various dots here are different methods we used for kind of reconstructing what the state is or making that photon measurement. And we actually do pretty well here. We're getting within a few % of the ideal spectrum. And there are also some neat things in another paper we've just recently submitted about sort of deconvolving the imperfections in this bitwise photon number measurement that go in. And maybe kind of at a high level, the point here is that this is a fairly simple molecule. Okay, still something you can calculate on your laptop pretty easily if you have a chemist to help you, by the way. But you see that it's also a very efficient hardware platform and a very short gate sequence, but it's not CNOTs and Hadamards. These are sort of natively bosonic operations. This is really a Gaussian boson sampling problem here that is applied to this particular case. And so this is a whole alternate mode of using these superconducting quantum hardware for that's different from the sort of traditional CNOT Hadamard spin a half type of quantum computer, and also different from the thing I'll talk about next week, which is using the cavity mode as the error corrected universal sort of two-level system computer. Now, by the way, we could reprogram. So the particular parameters that go into this gate sequence here are set by, again, the knowledge of what the potential energy surfaces in the molecule are. So we could do this for a variety of different things. We could do ozone. We could also do things which are harder to calculate in the conventional schemes. For example, if you started with 1 quantum in one of the vibrational modes and 2 quanta in the other vibrational mode, these are the Franck-Condon probabilities, or the predicted spectrum of the absorption of this molecule in this case. And we could do, again, with this simple platform, kind of anything that is in this particular symmetry class where there are 2 dominant modes in your triatomic molecule. And obviously, if you scale up to more modes, here you could do much more complicated molecules. Okay, so more examples of things we could do with this kind of reprogrammable quantum simulator. So let's see, I want to leave some time for questions. I'll just make one kind of final comment here. So as I mentioned, this is a different approach. You could do this same Franck-Condon calculation by doing a quantum simulation with a conventional qubit-based machine. So we don't compare well yet with classical computers. That's because classical computers have quite a bit of capability already. But how do we compare, for this particular problem, our bosonic approach with the traditional 2-level system approach? And I want to make a call out to Ike Chuang for helping us with this particular piece of this research. So first of all, your qubits are just 2-state systems. So if we wanted to encapsulate the up to 16 quanta in each of the modes, we would need several physical qubits instead of our 2 modes. We would need something like 8 qubits in total here to represent that state. But in addition, if you wanted to do effectively this vibronic simulation using spin-a-half elements and traditional circuits, Hadamard, C0, etc., it's possible, but it leads to an undesirable overhead. It would have taken, we estimated, several thousands of gates in a conventional quantum computer to get this same answer with comparable precision. And in our case, it was only like a total of 7 gates, or circuit depth 2 or 3, which is one of the reasons it already works quite well. So I think this is kind of an interesting perspective that I want people to take away, right? What does it take to build a quantum computer that's really useful, or to get quantum advantage? Well, more gates and more qubits, yes. But maybe not always just more. You also want to be smarter about how you use them. And we shouldn't necessarily just say we're going to engineer hugely massive qubit-based platforms and then figure out what to use them for. It's already the time to start thinking about what are the use cases, what are the algorithms, and how do you kind of match, as I said before, to get the most bang for the buck out of one of these quantum simulations, or out of near-term quantum computers that we'll have access to. So I think with that, I'm going to just thank the team. So I waxed on a little bit about the multidisciplinarity that this field is going to need and is starting to employ. One fun thing about this project is it was our usual gang of circuit QED hardware folks, some of our long-term friends in quantum optics theory that helped us, but really involved a very active collaboration also with true computational and physical experimental chemists, as well as important inputs from quantum algorithm and quantum information theorists. So I think this is certainly my first paper with a ball and stick model and a molecular spectrum in it. But I think also it's very fun to see now that the kind of things you can do when you bring together people with different sets of experience and knowledge, especially when they're the quality of this team. So I think I'll just finish there, and we have a couple minutes, sorry, for questions, but I hope you enjoyed it. Here's the references also to the paper on the measurements and this Vibronic spectrum calculation. Thanks.
Thank you a lot, Rob, for this very nice and inspiring talk. I liked especially your last part of showing that actually you should put more thought in the mappings, right? And just going through the brute force qubit way. So there are quite some questions, and let me just go through them as they popped in. So we have a question of Pau Ferreira. The kappa parameter in a cavity can be separated into two terms: the cavity outcoupling rate and the cavity loss rate. If one wants now to bring the electromagnetic field out of your resonator, the outcoupling rate should be much bigger than the cavity loss rate. And the question is now, how do these two terms compare in your system?
Ah, very good. Yeah. So maybe you know, in these simulations, it's a little bit like boson sampling, but we're using standing modes, right? So we never really, in these experiments, want to couple the field out of the cavities, except for when we're trying to do reset. And so what we typically do is we have a drive pin which is undercoupled. So and then we just use a strong classical drive in order to do things like the displacements or the drives we need for the optimal control pulses. Now, with these millisecond lifetimes, an issue is repetition rate. And we actually do have a way of kind of Q switching the cavities using this 4-wave mixing so that we can dump the states out and check if they've gotten back to the ground state so that we can you know, iterate the experiment more rapidly.
Okay. I have to go. We have many questions coming in. I try to sort them in a logical order.
So we can take them in however order they came in.
Yeah. The question is, how important is it to have these very high Q cavities for the experiments you presented? Would more conventional CPW resonators also be sufficiently good?
Yeah, you can do some of these things with the conventional CPW resonators. You know, those resonators are more compact, sort of. I think actually the size about the connectorization and how you bring the input and output signals to the device. You know, so when people show you the chip, usually they're just showing you the chip and not the whole package with all the connections. You know, in these experiments, as I mentioned, maybe this is the right slide. You know, it's important that for the fidelity of the simulation, that all of the things, including the squeezing, the beam splitters, and these optimal control pulses can happen quickly compared to the decay rate. So that's typically for us hundreds of nanoseconds to microseconds. So you can get, you know, planar resonators with maybe 50 to 100 microsecond lifetime, but these three-dimensional devices are always going to be better because they're always less sensitive to whatever it is that's limiting the internal Q, which is some combination of surface losses and defects. So I think it's always better to do it in 3D, but that's my personal perspective.
Maybe a very quick follow-up. There was a question by Piero Chiappina if these experiments could also be done by coupling to other bosonic degrees of freedom, for example, and that's the concrete thing here, phonons in mechanical oscillators. Right.
Yeah. So yeah, the whole field of nanomechanics, or we could call it circuit QED with phonons, you know, has been quite active and has made a lot of progress over the years. Now we've actually started a little bit at Yale to play around with this. So one can achieve the strong coupling limit, and several groups have done this, of let's say a transmon qubit to a variety of different microscopic phononic modes. At Yale, we do this to what are called H-bars. They're sort of vertical bulk acoustic resonances of the chip underneath the transmon. To date, the lifetime of those is not quite as good as the lifetime of these mechanical oscillators that we've used, is not quite as good as the lifetime of the microwave oscillators. And it's a little bit more challenging to get the strong coupling. Typically G's of maybe tens of megahertz or megahertz is state of the art, not hundreds of megahertz. So we're not quite as deep into all the strong coupling limits. And I don't think you could do quite this experiment yet with phonons. but it's an interesting perspective, and it offers a way to really miniaturize your bosonic degree of freedom. So it's interesting. It's a good question.
Okay, then there's one question that it's popping out a few times, for example, by Daniel Slichter and by Gerhard Kirschmeier. And the question is now more concrete on your on your molecule experiment simulation. So how can you actually change, or what does it require to change, to scale this up to more interacting modes to simulate more complicated molecules?
Right. Well, that's just scaling, isn't it? Yeah. I mean, there's you know, there are various challenges that you run into. I guess, you know, kind of at Yale, the most complicated experiments we've done are things maybe as shown here. Kind of, this is 4 cavities that can interact, and this device has the ability to have individual ancillas as well as nonlinear couplers between all of these devices in a ring. There are other organizations that are making bigger and more complicated versions of these things, but it's not easy to both increase the number of elements, the complexity of the control system, and manipulations and calibrations, and maintain all the coherences at the same time. So it's the same you know, challenges that everyone else runs into as well. But this is something where there's very rapid progress being made. So specifically, the way this needs to work is if you have n atoms in your molecule and there are no symmetry constraints, I believe 3n minus 5 is the number of modes you need, where n is the number of atoms to rep. It's basically, you know, you don't care about overall rotations of the molecule or translations in space. So anyway. Okay,
there's actually a second part of that of the question that I haven't read for actually on purpose, because the question is now, you discussed the scaling, but is it actually required for this particular problem that you have all-to-all connectivity between all your oscillators?
Right. Yeah. No, this is an interesting case. This particular problem has a kind of symmetry. Let me pull up. Yeah, this is maybe the best slide for that. This swap operation here between the various modes, you can efficiently decompose that, and a linear chain even would be fine and doesn't affect the scaling for this particular kind of problem. But that's only, okay, maybe I'm not sure this is a correct statement, but I think that's only really true in the case where you're making also this harmonic approximation for the modes. So, this one actually does not require all-to-all. Even nearest neighbor coupling is fine.
Okay. Then one last question to the molecule problem. Is there a difference to simulate vibrational modes or rotational modes?
It's a good question. I mean, the rotational modes are, I think, intrinsically always much more nonlinear, right? And again, here we've made a sort of harmonic approximation of these, which is not terrible in the case of the molecules I showed you, but is not fully accurate. Of course, with the Josephson junctions, you can include all kinds of nonlinearity, and that's what sort of part of the new directions here is, you know, what is the most interesting way we can add in some significant nonlinearity to the problem. You know, when you have a nonlinear or dissipative quantum simulation or quantum calculation you're trying to do, it's even more challenging, right? I guess many molecules have even more complicated structures where you could have, you know, full row vibronic couplings, and I have not thought about that problem. Maybe that's interesting. Good question.
Okay. Now, I think 2 more questions we have. One is error correction for the Fock states in the bosonic modes as efficient or inefficient as that on qubits?
Okay. I think that's more on the topic of a different talk, but so you can't error correct a Fock state. So 0 and 1, you know, if there's a decay, your information is gone. The way we do the hardware efficient error correction in these cavities is by using the multiple energy levels, multiple Fock states, to encode one superposition or one qubit worth of information, and to have a symmetry property or an additional bit of information that allows you to check whether there's been an error. So for example, the sort of most primitive code would be to use n equals 2 as one of the logical states, and the superposition 0 plus 4 with equal weights as the one logical. Those both have the same average photon number, and they both have definite photon number parity, and they are orthogonal states. And you can check if there's been a change in parity to odd, and that will allow you to figure out whether you've decayed without learning whether you were in the 0 logical or the 1 logical. So that's indeed much more efficient, because now you only had 4 energy levels in one object to do a full error correction of a single error syndrome, right? And there's now a theory of bosonic coding, and this is becoming a much more active area, both not just experimentally, but also theoretically. What they tell me is that for every error channel we would want to correct, we need to add only one more energy level in the oscillator that we control. And I showed you here that we're doing a decent job on even 16 energy levels. However, the particular code may be quite complex then, and detecting those symmetry properties or the stabilizers of those codes efficiently is, like, I think you can prove that it's mathematically possible, but somewhat challenging perhaps experimentally. The parity measurement we're quite good at, quite good.
Okay. And there was, let's finish with one last question, and that was about a route to achieve quantum supremacy or quantum advantage.
Right.
And it was especially mentioned in the context of boson sampling in your setup.
Right.
So yeah, maybe you can comment on this.
Yeah, so this is not, I would say, my area of expertise. We have talked to some of the experts about this. So, you know, I think standardly it's something like 20 or 30 photons, but in some larger number of modes, that is in the sort of linear optics platforms where you kind of reach the threshold of quantum supremacy. What is not completely clear to me is if we're doing this Gaussian boson sampling, or if we have the ability to use sort of more energy levels per mode, how that exactly affects supremacy. It may not really be that helpful, is what I'm gathering. But you know, it's not infeasible to imagine building systems with dozens of these modes. That's stuff we're actively working on. So, you know, we're not there yet, but I think it might be possible to do that. But personally, I'm a little less interested in quantum supremacy, especially if you're just showing a very, very tiny statistical effect, than I am in showing real quantum advantage. I would be more happy when one of the chemists says, you know, I learned something from that calculation you did. That, I think, is really where we could try to stay focused, rather than, I think at this point, I'm satisfied that quantum computers are theoretically much more powerful. What we want to show is they're actually useful.
Yes,
but that's me.
I think we agree. Good. Then thanks again for this really great talk, and for taking your time for answering all the questions. And I hand over to Sebastian.
Awesome. Thank you for the questions. That's great.
Thank you, Rob, also from my side for a very cool talk. And I'd like to finish up by making a few announcements as usual. So next week on December 10th, we will have Charles Adams talking about Rydberg atoms. And if you want to get notified about what we do, please go to our website, quantumscienceseminar.com. You can subscribe to our email list, to our Google Calendar, and you can follow us on Twitter. You should certainly check out our sister seminar, the virtual AMO seminar, where tomorrow they will have Ashish Clerk on driven dissipative quantum systems. Next week, our speaker today, Rob Schoelkopf, will give another talk on quantum error correction, as he mentioned. If you want to join us for a Q&A session with Rob, please dial in with the Zoom link using the link that I'm going to paste into the YouTube chat window in a second. Thank you for your interest, and we hope to see you again next week, same time, same place. Bye.